When doing double replacement reactions, some products automatically break down again to form a gas. So gases may form directly in a double replacement reaction or can be formed from the decomposition of a product, such as H2CO3. So never leave H2CO3, H2SO3, or NH4OH as products of a double replacement reaction. And again, that was products. If they're reactants, then that's fine. They're going to stay as that as a reactant. But as a product, they're going to further decompose. So carbonic acid further breaks down into water and carbon dioxide gas. Sulfuric acid will break down into water and SO2 gas, or sulfur dioxide. And NH4OH breaks down into water and ammonia gas. So let's see how that works. Here we have some double replacement reactions. So remember, the first thing we want to do is figure out our charges for each of our parts. And then outside, inside go together. So sodium should be going with chlorine. And based on those charges, we get NaCl. And then hydrogen goes with with SO3. And they go together like so. But remember, H2SO3 was one of the ones we just saw on the other page. So once I write that, I need to break it down and say, oh, that doesn't exist. Really, it's going to be water and sulfur dioxide. Water is going to be a liquid, and sulfur dioxide is a gas. To figure out my state symbol for sodium chloride, since that's an ionic compound, I would look at my solubility rules, and all Group 1A are soluble, so I know that's aqueous. Let's look at one more together. So on this second example, we have our +1, -2, +1, and a -1. So my K goes with NO3, and then I get H2CO3. If you recognize that you're making one of those three compounds, you don't have to write it and scratch it out. You can just write it directly from there. But again, this one doesn't exist, so that's going to turn into water and carbon dioxide when it's getting formed. Water is a liquid, carbon dioxide is a gas, and according to my solubility rules, potassium nitrate would be aqueous because it's group 1A. I'm going to pause the video and do these next three on your own. Restart when you are done. So for C, you should have gotten ammonium hydroxide, which then you should have broken down into ammonia, which was a gas, water, which is a liquid, and NaCl, which is aqueous. D was a little tricky. We have iron 2 chloride, which is aqueous because all chlorides are soluble except silver, lead, and mercury. And then we get H2S, which looks like it's a weak acid, but H2S is actually a gas. That's going to be hydrogen sulfide gas. It's responsible for like a rotten egg smell. So even if you didn't recognize that that was a gas, you would say, oh, well, that's a weak acid, which would be insoluble. So if we were doing net ionic equations, you would still keep that together. But just know that H2S is a gas, but it didn't have to break down to produce that gas. And so for the last one, we have strontium sulfide, and we don't have a rule for strontium or sulfides, so we're going to say that's a solid. It is slightly soluble, but we're going to say that's a solid since we didn't have a solubility rule for it. And then ammonium hydroxide, we said earlier, breaks down into ammonia, which is a gas, and water, which is a liquid. We can also have acid-base reactions. When we have an acid and a base, that's a neutralization reaction. So the acid is going to react with the base to produce a salt. A salt is simply an ionic compound. that's formed from an acid and a base. When we get to net ionics, remember that strong acids and strong bases should be breaking up 100%. All right, so for this first reaction, is that an acid-base reaction? Well, we have an acid, but do we have a base? So this doesn't end in hydroxide, so it's not our traditional base, at least. So this is not an acid-base reaction. But we can break it apart and still do our solubility rules all the same. So sodium chloride is soluble. And then nitric acid is a strong acid, so that would also break apart. The next one is an acid-base reaction. It's just not a Arrhenius acid and base, which means it starts with a hydrogen as our acid, but this is acidic. When we get to acids and bases, we'll discuss this reaction more at that point. But in this case, all we need to do is double replacement to determine our products. Up, we made ammonium hydroxide, which means we're really making ammonia gas, water, and NaBr. And then this last one is our traditional acid-base neutralization reaction. So we make water in an acid-base reaction. And then we make some salt, in this case potassium oxalate. It's a group 1A, so it's going to be soluble. So titration is a process in which a solution of known concentration, the known concentration is our standard solution, is added to analyze another solution that we don't know the concentration of. So some vocab words, we have a titrant, which is the solution of known concentration. We're generally going to put that in the burette. The equivalence point or stoichiometric point in which just enough titrant has been added to react with the substance being analyzed. So at this point, we should have equal moles of acid and base. An indicator is used many times so you can see where the equivalence point is. So here in the picture, we're adding our titrant to our solution, and then whenever we see this color change, we know that we're done adding our titrant. We know this one's molarity, and then we know how much volume was needed to get to this place where we have equal moles of acid and base. And so the end point is when it changes color. So using titration, the molarity of the unknown solution can be calculated from the volume and molarity of the standard solution that was used. We can use stoichiometry and write a balanced equation and do it that way. But a shorthand way is to use this equation. So the IA and IB take into account what the coefficients would have been on each other if you had written the balanced equation. So IA is the number of hydrogen ions on the acid. IB is the number of hydroxide ions on the base. So basically that stands for ions of acid or hydrogen and then ions of my basic ion, which is hydroxide. VA is volume of acid used. VB is volume of base used. MA is molarity of acid and MB molarity of base. It doesn't matter your units for volume as long as they equal. So if one's milliliters, the other one also has to be milliliters. So for example, here we have our base and here we have our acid. So we have our equation IA, MA, VA, so my IA, I look at my acid and there's 2 hydrogen ions. So that's going to be 2. My molarity of my acid was 0.500 molarity. And my volume of my acid was 21.7 milliliters. My IB, I've got 3 hydroxides. I'm trying to find the molarity of my base, and the volume of my base was 26.4. So now I just do algebra to solve for my molarity of my base. So 2 times 0.5 times 21.7 gives me 21.7. And then 3 times 26.4 gives me 79.2 molarity. So then I divide. We wanted 3 sig figs. So my molarity of the basic solution should be 0.274. We know that it's an acid-base neutralization or equivalence if I see the word neutralize, equivalence point, titrated with. Any of those are going to tell me that I'm going to do this equation. So I'm going to pause the video and do this one on your own. Restart when you're done. So on this problem, our IA, there's only one hydrogen ion in front, so we have a 1. Our molarity should have been 0.1. And our volume was 54.6. On the other side, our IB was a 1 as well. We don't know the molarity, and our volume is 25. So solving that out, you get 0.218 molarity.